So let's gonna do this one. I love this book. Okay, so for me, it's my favorite book regarding thermodynamics, and it has some very interesting problems. This is a very good problem in order to talk about something that it seems like a Brayton cycle. It is not a Brayton cycle. It's just a turbine, gas turbine, and a compressor. Okay, where the air is entering at these conditions, it's leaving at these conditions. It goes into a diesel engine, and then it goes from the exhaust of the diesel engine at these conditions, and it gets out of the turbine at these ones. Okay, so you have some sort of information regarding this. It's actually a turbocharger. Okay, well, and it's not a Brayton cycle, but you can think of this as if it was a Brayton cycle in the sense that you are working with an ideal gas, you're working with a turbine, and you're working with a compressor. So let's go and put the data of this problem. Okay, I'm gonna call this thing 1. This guy is gonna be state 2. This one is gonna be state 3, and this guy is gonna be state 4. Okay, the fluid is gonna be air, although it changes a little bit. At this point, let me just try to be more specific. This one is gonna be air, okay? So from air here, but it goes out, not just air, it's actually what is going out of this diesel engine is just exhaust gases. Well, it makes a difference. The problem is actually making a difference. So I'm gonna put gases, okay, just like that. But I'm gonna call that, when I'm putting some variable over there, I'm gonna call it exhaust gases, okay? So exhaust gases. And it's gonna be a call an A, an E. I'm gonna use an E for that one. I'm gonna use an A. So let me just put data regarding that. So I'm gonna use the constant for the gases, which is gonna be for air 0.287 kilojoules per kilogram. So what I'm doing right now is put data. Let me just put it. This thing is data. So what else? Ka, this is the adiabatic index, 1.4, got it. And then what else? So CPA, this is what I did, okay? I'm gonna tell you later how I got this other parameter, which is the specific heat for constant pressure, okay? Kilojoules per kilogram Kelvin. And that's it. Now for the exhaust part, I have this data. This is actually raw data from the sentence, 0.29. I'm gonna tell you later what they're asking you to get. So Ka is 1.32, and then CPE equals to 1.19625. Okay, so these ones are calculated by me. Okay, so I may be wrong. This is not just raw data. I got this from the information that I have about how can I do it? Well, I think I can remember that K is equal to Cp divided by Cv. This is for any ideal gas, actually for a perfect gas. And then also, you know that Cp minus Cv is actually this for an ideal gas. Therefore, what you can do is use some algebra, because you don't know this stuff, you don't know this stuff, you don't know these two guys, but you know these guys because those are, again, raw data. Therefore, with this combination of stuff, you can get to that Cp equals to R divided by 1 minus 1 divided by K, okay? So that's how I got these two fellas over here, okay? It's just some algebra with this raw data that I have here, and that's what I can get. Now, there is more things, okay? Water. Let me just think about how can I put it. Yeah, I'm gonna tell you what they are asking you to find. So find this. For problem A, there are two problems in this one. If it says so, that the isentropic efficiency of the compressor equals to 1, and the efficiency of the turbine, oh my God, the turbine equals 212, that is, if these two machines or devices are isentropic, that is ideal, they work ideally or reversibly. It's not the same thing, but so far we can say that because I'm actually thinking these two guys are adiabatic. Therefore, find pressure at 3. And you will say, oh, what does that have to do? Well, it has to do with something. Now B, now they are just changing the stuff. If the isentropic efficiency of the compressor is 0.7 and the isentropic efficiency of the turbine equals to 0.8, I think it's 0.88 is, therefore find again P3. You will say, well, does it change? Yeah, it changes. How so? Well, we're gonna find out why does this P3 value changes, okay? So this is a problem that we have at hand, okay? I have some data over here and we need to find something out. So I won't bother to put again this stuff, but I'm gonna jump right into the problem, okay? I don't know if I'm gonna solve it directly by doing that, but this is my way to work when I'm having this type of problems regarding ideal gases and isentropic or not isentropic turbines and compressors, okay? So I'm gonna do this. I'm gonna start by doing the process that goes from 1 to 2, but if the process was isentropic. This little s as a sub-index over here means that I'm doing the isentropic process. So the first exercise is telling me, yeah, it's isentropic. Okay, I'm saying fine, but it doesn't really matter. I'm gonna use this same data that I'm having over here, this same calculation that I'm doing here. I also need it for the B part of the problem, because you cannot go to the real problem, okay, that is real because it has some efficiency that is not equal to 1, that is for real machines. I always need to pass, or most of the times I would say, I need to pass through the isentropic process. So it's just a way of doing this type of problems. My way of saying it, when I said to my student this, is that you need to always go through the isentropic process. Whether you have an ideal process or not, you always need to do the isentropic process. Why? Because it will give you information for later. Well, okay, so that's what we're going to do so far. So for an ideal gas, I can write this. P1, 1 minus K, T1K equals to P2, 1 minus K, and T2S. Why did you put T2S? Because what I want to find over here is what is the temperature if the process was isentropic. That's what I'm telling you. So what I'm doing here with that equation that I have below here is just this. I have put the isentropic part, which is the same thing as putting this 1 PV1K equals to P2V2K. Okay, it's the same thing that I have put down there. Okay, so if you remember something about ideal gases, this is the same thing as putting an adiabatic case. Okay, now it's a little bit confusing, but for ideal gases, you can say that the adiabatic process has the same expression as the isentropic process. You actually can prove that. Well, okay. So what I'm doing here is to get that 2s, and hopefully it's not the algebra is not that difficult for you. It is a little bit of it has its tricks, but nonetheless, I think I can write it. And this is for air, okay? So I should be putting A, and A because I'm gonna use the Ka part, okay? I'm not using Ke because I'm doing from 1 to 2, and from 1 to 2, I'm sure that this substance is air. Now from 3 to 4, I'm gonna use the parameters or the values for the exhaust gases, not for the air. Okay, now having said that, I'm gonna calculate it, and maybe you see that this thing's gonna be, look at it, it's 1 divided by 2 atmospheres, 1 minus 1.4 divided by 1.4, and T1 is actually 300 Kelvin. 300 Kelvin. Now from that calculation, my answer is that I have 365.7 K, okay? So you check that out and tell me if that's wrong, that thing may be wrong in the comment section, okay? So first step to get this T2S. What is this? Is the temperature at the outlet of the compressor if the compressor was isentropic. For our A case of this problem, it is an ideal compressor. So far, this is what I have for the at the outlet of the compressor in the first part of the problem, which is the problem or the part A of the problem. Well, now what? Now I can do this. Maybe you agree with me, but I can put an expression for the energy balance for the compressor, which is this one. Okay, I'm having that. So that's what I have over there. It's just energy balance for the compressor. Now the details, I'm just keeping those because for this part of the course, maybe you need to know how to get this stuff. Please notice that you don't have this stuff. Okay, you don't have it. You have this one, you have this one, and now you have this one. But I can do this. I'm going to divide everything by MA, okay? Therefore, I will have the CPA times the T2S minus T1, which is actually one thing that I can get. This guy is 0.0045 times, 365.7, which is minus 300. So overall, I have this. Maybe for the next one, I won't put all this expression. I would just skip to the value. But so far, let me just put it. It's approximately 66 kilojoules per kilogram, okay? Hey, what did you get this? Well, maybe I need it, or maybe I don't. Doesn't really matter. So far, I'm just collecting some information that I may be needing later. Well, okay, good for me. Then what? Did you end it? No, not at all. So what are you doing now? Now I'm gonna skip to the other device. The other device is, I'm gonna use this now, this one. From 3 to 4. So I'm doing the isentropic, again, this is isentropic. I'm doing the isentropic case for the turbine. Okay, why? Well, maybe it gives me some information that I needed. Okay, so I'm thinking that in this case, the turbine is isentropic, which it is in this part of the problem, and then I'm gonna get some data. Maybe P3 1 minus KE, okay, T3 KE, sorry, equals to P4 1 minus KE and T4S. Why? Because after an ideal turbine, you will get an ideal outlet temperature for that turbine. Okay, so you will get that KE over there. Now, let me try to put in explicit form the T4S, which is going to be equal to P3 divided by P4, 1 minus KE divided everything by KE times T3, okay? So you have T3. Yeah, let me just check it. Yeah, I have T3 over here. So that's data. Then what? KAE, I already have it, so easy peasy. Now P3, no, you don't have it. This is the one that they're asking you to get it. You don't have T4S, so this is so sad. And P4, you already have it. Let's just go back here and you have what's the pressure at the outlet of that turbine. Well, okay, so far you are there, okay? You cannot get any more information out of this proposition. Now, what I'm going to do here is something that maybe you agree with, just energy balance for that one. What do you mean by that one? I mean by that machine. ME, exhaust gases, CPE, exhaust gases, T, let me just put this thing as positive, okay? So we have discussed this positive, negative stuff for these machines. So I'm putting this as positive for this case, okay? So I don't have this one, I have this one, I have this one, and I don't have this one. But it is okay, so this thing was wrong for my part. It is part of the problem. It's raw data. It's telling you something. It's saying that at 3, okay, so at 3, what you have is 4% more. Let me just put it in that way. 4% more of mass flow, okay? So due to the combustion, okay, what you put into the diesel engine, you put fuel into it. And that fuel will add to the mass flow that you got from 2. So what I can write as an equation is that the M of the exhaust gases, the mass flow of the exhaust gases, is actually 1.044% more than what I got at the beginning, at the beginning of the year, okay, at the beginning of the whole process. So this one, it's an important part of information, okay? Sorry, that was my bad. Now, this is when I was doing this 1 to 2s, I didn't need that information. When I'm doing 3 to 4s, I don't need that information. But now I needed that information. Look at it. So what I can do here is this. I can put the power of the turbine is going to be 1.04 of the mass flow of the air. Okay, that's correct. CPE is still the heat capacity of the exhaust gases. T3 minus T4S. Okay. So after this, you have an expression for this. You don't have this guy, but you have this, and you have this, but you don't have this guy over here. Now, let me just do this. If you see the figure over here, maybe you see that whatever the turbine is producing at work or as power, okay, is going, the whole deal is going to the compressor. There is no generator, electrical generator over there. That's the whole deal of putting a turbocharger. So whatever you're doing here, whatever power you are getting out of the turbine, you are putting that into the compressor so that you can put more air into the diesel engine, and you will increase the efficiency of that machine, of that diesel engine, okay? Therefore, what you can actually write from the beginning is that all of the power of the turbine equals all of the power of the compressor. Therefore, let's just go back here and say, well, okay, so I can put this equation over here. Therefore, you will get this. Maybe you see it, that 1.04 MA, okay, CPE, T3 minus T4S should be equal to whatever I have put over here. So I'm going to put it again. Hey, what did you do this? Therefore, you're just wasting time by doing this and getting that. Well, let me see if I just wasted your time by doing that. So MA, CPA, T2S, oops. Let me just put it like that. Oops, this. So T2S minus T1. Okay, so what I'm gonna do here is divide everything by MA. Okay, so whoops, it just goes. And what I have over here is that I know it, 1.04, I know it. CPE, I know it. T3, I know it. I don't know the T4S. I know this guy, I know this guy, and I know this guy. Actually, I know all this stuff, okay, which is 66. Therefore, I'm gonna put this 1.04 CPE should be equal to T3 minus T4S equals equals to 66. Now from this, or from here, this is my only unknown. Therefore, I'm gonna get it right away, okay? So I won't deal into the details of the algebra, but what I have out of that is that you can find if we are right or wrong. What I have found over that is that T4S equals to 796.95 Kelvin. And this is completely meaningless so far. I mean, it will help me to get all the other stuff, but so far it's just nothing, okay? It's not actually helping me to get anything out of that. Well, okay, so that's what you're doing so far over here, okay? Now let me go to, okay, so here, I'm just wasting bitmaps. Well, okay, so T4S. And then what? Well, what I can do over here is to maybe find this fella over there. Well, maybe I can get it. Or maybe I can get something like that. I can get it. This is what I can get. Oh, and you will say, hey, why would you get it? Well, maybe because I can, okay? I can get all this stuff, but maybe you don't actually need it. What you need is to get this P3 over here. This is what they're asking you to get. So now you see that I can go back to this place and maybe get everything that I need. Let's just say again, so P3, 1 minus Ka, T3 KE equals to P4. I'm just doing the same thing that I have done, so hopefully I'm not boring you. KE. Let's just see what you have over here. I have this guy. I have KE, 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 KE. I have P4 and I have T4S. Now I can get this fella over there. Therefore, what I can write is that P3 equals, I'm just going to present you the equation that I got there, but it's not that important so far. T4S divided by T3, and this is gonna be KE divided by 1 minus KE, multiply everything by P4. Okay, so with this information, you can put it there. You have everything you need. Okay, it's not a problem. So what I have over here is 1.304 atmospheres. That's what I have at the end of the diesel engine if the compressor and the turbine are isentropic. That's what I can say out of this stuff. So this is my answer for problem A. Okay, so good for me. Let's just go and do problem B. Problem is a little bit more complicated, but nonetheless, let's just see if we can find it. So what we have, I'm just going to just do this stuff over here. Just kind of separate all this stuff. Oops. So in case we needs to have some of that issue over there. So let me just do this. Let me make myself some room over there. So let's just do the B stuff, okay? Again, this is what I will do. I will do 1 to 2s, okay? But I already did that stuff. So I have found out that T2s equals to, so I got it here. It's actually T2s equals to 365.7 kilojoules, like kilojoules here, sure, buddy. This is just Kelvin, okay, so Kelvin, okay? So what are you doing this again? Now, because now I can use the information because now the efficiency, isentropic efficiency of the compressor is 0.7. So if I have that information over there, therefore I can write the expression for the efficiency, which is work divided by work. And I have never known this by memory. I need always to do this. So I will do it again. A compressor always needs to be supplied with more work, so it needs to be the real part down there, than the ideal compressor. I'm gonna put compressor, but the ideal part, okay? Now that I have that, I can put, this stuff, MACPA, T2S, YS, because this part is the isentropic part, minus T1. And I'm gonna divide everything. I won't do this again, but just to show you how I got my stuff. So T2R minus T1. These two fellas just goes out, up and down, okay? So they are eliminated, you just divide by it. You have this value, and you already have this value, but you don't have this one, so let's just get it. So now from that part, I will get that T2R minus T1 equals to T2S minus T1, divide everything by the efficiency, which is 0.7 in this case. So with that in mind, you can get T2R. And T2R, according to me, is 393.857 Kelvin, okay? So this is the actual temperature out of the compressor if it was 70% efficient, okay? This is what I have at the end or at the outlet of the compressor. And it's before going into the diesel engine. Okay, so what is that good for? Well, now maybe, I can write an expression for the real or the actual work received by the compressor, which is equals to MACPA times T2R minus T1. Okay, so not, yes, yes, and yes. Okay, therefore I can get something out of that, which equals to the specific work of the compressor. In this case, I have the number. Yes, I have the number, and this thing is going to be 94.28 kilojoules per kilogram. Notice that I need to supply more work for an actual compressor than for an ideal compressor. For the ideal compressor, it was 66 kilojoules per kilogram in order to do the same job, but now for the real compressor, I need to add 28 more kilojoules in order to run the machine. Okay, so that's one of the lessons of the entropy generation. It's actually done by the entropy generation. That's why you need to add more work for a not so perfect machine. Okay, well, okay. And so what? Well, nothing. Now let's just go for the 3 to 4s. But you have already done it. Yeah, I know. So P3, 1 minus KE, T3 KE equals to P4. You already did this. I know. Be patient. T4s KE. And this is not actually your problem because you already done something about it. Well, so what? Why are you doing this again? Well, I'm just doing it again because I need some structure. And out of this, P4, you know it. T3, you know it. T4s, you don't know it because the P3 has changed. So maybe if you put again the T4s, oh, it's wrong. I don't know if you see that. Well, maybe that's what this is what I'm trying to infer from this equation. This P3 needs to change. Maybe I'm thinking this now. In this case, it's going to change. So if this guy changes, this T4s needs to change because T3 is fixed and P4 is fixed. Therefore, you will say, oh, so the ideal case is going to change. And I maybe say, yes, it's actually going to change. Well, let's just see if that thing actually happens or not. So now, what I'm going to put over here from here is that, what am I going to put from here? Well, let me just put this. This is still true, okay? This hasn't changed. This equation hasn't changed. Therefore, what I can write is that now for the real part, it will look like this. Well, I'm not doing anything brilliant, okay? But let me just put the stuff. So MECPE T3 minus T4R equals to MACPA T2R minus T1, okay? Okay, so let me just do again what I did in the other problem, 1.04 MA CPE T3 minus T4R, therefore MA CPA, you know, same stuff. Well, kind of same stuff because yes, now I had this one. Now I have this guy over here. So yes, but I'm gonna divide everything by MA. Why? Because I need it. Therefore, you don't know this stuff. I don't know this stuff, and I don't know which other stuff do I don't know. So yes, I know, and yes, I know. Therefore, I'm gonna get T4R. So T4R is actually, well, I'm not going to do all the stuff over here, but believe me, or you can do it, and maybe tell me if I'm wrong. This is like that, okay? So got it. What have you found? What I have found over here is this T4R. I already have found that. Well, okay, now what? With this information, you can go back over here and well, no, because out of this equation, you will get some isentropic information. And this T4R is actually an actual temperature outside of the turbine. Okay, so maybe it's not a good idea to put it over here because out of this, you are actually waiting for something that is isentropic. Therefore, you need to use this. So the efficiency of a turbine is, I never do this by memory. I always need to do it again and again. So it's work divided by work. Now I need to always think about it. So the turbine, I will never be able to get more work out of an imperfect machine than from a perfect machine. Therefore, what I have over here is that the real part, let me just put TR, let's just do it again, because I put that R. So the power or the work due of a turbine, the real part's always gonna be less than what I can extract from a perfect or ideal turbine. Okay, so if this thing is correct, I already know that the value is 0.8 according to the problem. Therefore, I can write something like this. ME, you know this stuff, and T3 minus T4R, okay, divided by MECP. No, E, it's this guy is E, but now it's T3 minus T4S, okay? So these guys will just go. This guy I already have them. I already have this T4R, but now the unknown is the isentropic one. Look at this problem. It's a really interesting problem. Most of the times you always get the isentropic part and then go and get the real part. But now in this case, just because of the data as you have it, you need to go do it backwards. That's why I love this freaking book, because it's so smart in the case of how they formulate problems. Well, okay, so what I will have now is to get the T4S. So T4S is going to be, I already have done all the algebra, and T4S is actually 755.27 K. Okay, so 755 Kelvin. Is that correct? Let me just go and check it with T4R. Well, maybe you know that T4R needs to be higher than T4S because you have not extracted all the energetic use in that machine called turbine. Okay, this is what you want to do. But outside of the turbine, or at the outlet of the turbine, at the exit of the turbine, what you have over there is a higher temperature gas. The ideal stuff is to have the coldest the gas is, the more juice you have extracted from the energy orange. Okay, that's what I mean by juice. The energy orange of the gas as it entered the turbine. Okay, so this thing is correct, and it has some logic out of these figures that I have over there. Okay, now with that information, now I can go and put it over there. And with that, I'm gonna get the P3. Oh, so P3 again is equals to a T4, let me just put T4S divided by T3, okay? And 1 minus K, no, it's not that way. So let me just erase that. It's actually KE. We have already done this, but I always need to do it again because I need to use my brain. So KE, not in the best way sometimes, KE divided by 1 minus KE times, now everything is multiplied by P4, okay? After that, you will get that you can put all the stuff over there, and P3 is gonna be equal to 1.628 atmospheres. So when you have two imperfect machines, it seems that the pressure that you need to put out in order to feed the turbine so it can feed a compressor so that you can have a turbocharger. So it seems that you need to increase the pressure, the less efficient these machines are. It's a nice freaking infer. So it's a nice lesson for this type of problem. So I love this book again, and I will I will do more problems regarding this book, also out of this book, but it's such a nice problem, okay, in that sense. Okay, guys, so enough of today. So see you guys around. Whatever comment you have, you can do it in the comment section. So see you guys, stay safe.